Hey everyone, and welcome. Today, we're cracking open those little devices that power our entire world to really understand the incredible science that's packed inside. We're talking about batteries and how they somehow turn simple chemical reactions into electricity. So let's get right into it.
Think about it for a second. Your phone, your remote, your car, even that little watch on your wrist, it all runs on batteries. But have you ever stopped to wonder how exactly that tiny metal can makes everything light up and go? Well, that's the big question we're going to answer today.
All right, here's our game plan. We're going to start with the basic science, that electric spark of chemistry. Then we'll look at the fundamental blueprint for every battery. From there, we'll check out the single-use batteries, then the rechargeables, and we'll finish up with a look at a technology that might just power our future.
Okay, so before we can even get into batteries themselves, we got to talk about the science that makes them all possible. And it all boils down to one fascinating field of study.
And that field is called electrochemistry. At its heart, it's really just the science of turning the energy locked away in chemical bonds into a flow of electrons, which, we call electricity. It's the magic bridge that connects a chemical reaction to an electric current.
So how does electrochemistry actually get the job done inside a battery? Well, it all comes down to a fundamental design, this elegant little engine called the galvanic cell. A galvanic cell, you might also hear it called a voltaic cell, is the absolute core of any battery. Its whole job is to take a chemical reaction that wants to happen all on its own, a spontaneous reaction, and to harness that energy, turning it into a useful flow of electricity. Now, this table is awesome because it really clarifies the galvanic cell's role. It's the total opposite of an electrolytic cell. An electrolytic cell uses electricity to force a reaction to happen. But our galvanic cell lets a natural reaction create electricity. And notice that the anode is negative and the cathode is positive. That's the key to getting our current to flow in the right direction. So let's see this blueprint in action with a classic example, the Daniell cell. On one side, we have the anode. Here, a solid piece of zinc literally gives up 2 of its electrons. This process of losing electrons, we call that oxidation. And that's what gives the anode its negative charge.
So where do those electrons go? Well, they travel through a wire over to the other side, the cathode. Waiting there are copper ions, just floating in a solution, and they are more than happy to grab those incoming electrons. This process of gaining electrons is called reduction. And that flow, that journey from anode to cathode, that is the electric current that powers our world.
Okay, with that blueprint burned into our brains, let's look at our first major category, primary batteries. You can think of these as the one-and-done batteries. They're designed for a single chemical reaction that can't be reversed. The most common one is the good old dry cell. Yeah, the one that's probably in your TV remote right now. The zinc can on the outside isn't just a container, it's the actual anode, giving up electrons. Those electrons are then picked up by the carbon rod in the center, the cathode, in a reaction with manganese dioxide. Once all that zinc gets used up, well, the battery's dead.
Now let's move on to another primary battery, the mercury cell. You can see right away from its compact design why it was so perfect for small devices where you need a consistent, reliable power source, like in watches or hearing aids.
The secret to the mercury cell's success was its incredibly stable voltage, right around 1.35 volts, and this slide shows you why. The overall reaction doesn't really change the concentration of the ions in the solution, and what that means is you get a nice, steady, consistent output for pretty much the battery's entire lifespan.
But what about the batteries we don't just throw away? Let's dive into secondary batteries. Their superpower is that their chemical reactions can actually be reversed. Yep, they're rechargeable.
And the undisputed king of secondary batteries has got to be the lead storage battery. This is the heavy-duty beast under the hood of your car. This picture gives you a great look at its internal structure, with all those alternating plates of lead and lead dioxide.
So when you start your car, the battery discharges. Both the lead anode and the lead dioxide cathode react with the sulfuric acid, and they both become lead sulfate. But here's the magic. When you recharge it by driving, your car's alternator forces that reaction to run backwards, turning the lead sulfate back into lead and lead dioxide, ready to go for the next time you start your engine.
Another really important secondary battery is the nickel-cadmium, or Ni-seed cell. As you can see from this cool jelly roll design, it's built for portability. These typically have a longer lifespan than lead-acid batteries, but they're also more expensive to make. So what's actually happening inside that jelly roll? Well, as it's powering your device, the cadmium is oxidized. It gives electrons away, while the nickel compound is reduced, taking them in. But the rechargeable magic is when you plug it in. Applying a current forces that reaction to run backwards, basically resetting the chemicals so you can use it all over again.
Okay, for our final category, we're looking at something that's not quite a battery in the traditional sense, but it's a type of galvanic cell with just enormous potential, the fuel cell.
This is a real game changer. Fuel cells don't store energy, they generate it on demand by converting fuel directly into electricity. So, as long as you keep supplying fuel, they keep producing power. This is the same incredible technology that provided both electricity and drinking water for the Apollo astronauts on their way to the moon.
And they are ridiculously efficient. A typical power plant that burns fuel might be about 40% efficient. A fuel cell, though, can convert that chemical energy directly into electrical energy with up to 70% efficiency. That is a massive improvement.
And this shows just how elegant the most common type is, the hydrogen-oxygen fuel cell. Hydrogen reacts at the anode, oxygen reacts at the cathode, and just look at the overall result. The only byproduct is pure water. That's it. It's a completely pollution-free way to make energy.
So, from the single-use dry cell to the rechargeable workhorse in our cars, all the way to the continuous clean energy of fuel cells, we've seen how chemistry creates power. The only question left is, which of these incredible chemical engines will you be relying on tomorrow?